The relevance of the Antoine equation as it relates to the phase diagram of a pure substance. So here I have the phase diagram of a pure substance and the Antoine equation. So the Antoine equation states that the log base 10 of the pressure is equal to A minus the fraction B over C plus the temperature. So what this means is that, say you were given a pressure, like a pressure right over here maybe, and you wanted to know at what temperature you were going to find the vaporization curve. We're going to have equilibrium between the liquid of your substance and the vapor of your substance. So you could use this equation for that, assuming that there are A, B, and C values that have been experimentally determined. If not, you would have to run experiments to find those values yourself for the specific compound that you're looking at. And if you were given a pressure, you could just plug it in and it would give you a temperature. Or vice versa, you could be given a temperature and use it to find the pressure at which you'd be on the vaporization curve. Alright, so the next part of our problem is going to be dealing with the nonlinear regression. So first I'm going to explain what that looks like. So as you can see here, I've made a plot with some random data on it. So say this is data that you're given and you're wanting to find some sort of model that's going to best fit this data so that you can predict other values in the future. So you could do this by linear regression, or you could do it by nonlinear regression, which is what I'm going to show you right now. So what this means is we're going to want a model that looks something like that. And as you can see, each of these points, most of these points, do not lie exactly on the model. There is some error associated with the data. So for example, this point, there's about that much error below the line. And this point here, there's about that much error above the line. So some are below, some are above. And there's error. So when we're wanting to do a regression, we want to minimize this error. We want to make it as small as possible because we want our model to be as accurate as possible. And the more error, the less accurate the model is. So we're going to look at this point right here. And so the corresponding point on the model would be that one. And so you can see both of these have an x value right here. We're going to call that xi. And these have two different y values. So I'm going to need to make my y-axis a little bit bigger. Okay. So this one is our model, so it's going to have y value right there, and we're just going to call that y. And this one is our data point, and it's going to have a y value right about there, so we're going to call that y sub I. So the error between these two is going to be y minus yi, because that will be that length right there. So we're going to have y minus y sub I. So that's the error for that one point. We're going to want the error for all of these points, not just the one. So we're going to want some sort of summation. However, if we leave it just like this, where we're only summing up, these differences, then values that are below the line, values that are below the line and values that are above the line will kind of like cancel out, which isn't what we want because both are error, both are bad, I guess, and we want to minimize that area as much as possible. And so if we cancel it out, we're not taking it into account, which is not what we want. So a couple ways there are to do this. We could take the absolute value of this, just like that. But the more common way to do it is not to do the absolute value, but is instead to square this whole thing. Then we're getting, because anything squared is going to be positive if it's a real number, which these are. And so then we're going to get the some square error of all of these points. And so then what we can do is we're going to take what we want our model to look like. So in this case, we might say our model is, y equals mx plus b. For this specific point, it'll be xi. And then we can take that and plug it into the summation. We're going to have the sum of mxi plus b minus y sub I squared. And we're going to want to find the values for m and b that minimize this function right there. Alright, so the next part of our problem says fit the experimental water vapor pressure data on our GitHub site to the Antoine equation by nonlinear regression. So over here is our water pressure vapor data, and I have opened up a blank Python script where we will solve this problem. And I've labeled it nonlinear regression so that we know that we are doing this by nonlinear regression, and I'll show you how to do it by linear regression later. So first thing we're going to need is we're going to need to import some of our libraries so that we can do more functions within Python. So to do this, we're going to go import numpy as np, and that is like a matrix laboratory kind of thing. And then we are going to want to make a plot of our data so we can see how our regression works, right? So from plotly.subplots, we're going to want to import make subplots. Alright. And then finally, for nonlinear regression, we're going to want to minimize the function. So from scipy.optimize, we're going to import minimize. So we can shift enter on there. So now we've imported these libraries and we can use them in our commands. So next thing we want to do is load in our data. So we can do that using the the !wget command, and then we can take this link for our raw data and paste it there. Alright, so now we should be able to see over here, we now have the data. So that's the water vapor pressure data, and there it is. But we're going to want to load this into a variable of some sort, so let's just call it data. And np.load text, and we're going to, so the title of our file is water vapor pressure.csv. And then over here you can see that all of the values are separated by commas, so that's our delimiter in this case. So we have to specify that. So delimiter is equal to comma, shift enter. Okay, and then let's just check to make sure that data loaded in correctly. And there you can see we have our data, 2931 and then 2.4, 2931, 2.4, so that's our data. Alright, so then we're going to want to split up this data. So you can see we've got the temperatures and the pressures all in one variable, but we're going to want separate variables for those. So let's go. We can call this temp for our temperatures, and we're going to want data. We're going to want to splice this, and we're going to want to take all of the rows, but only the first column. And since indexing starts at 0 in Python, first column is column 0, right? And then we're going to want our pressures, so we'll call that press, and we're going to want data, and we're again going to want all of the rows, but only the second column. And again, since indexing starts at 0, this will be column 1. Alright, we're going to shift enter on there, and then let's make sure that worked. Right? So we got 2.315, 303, so it's 2.315, 303, and then, so those are our temperatures, and then let's check the pressures. We got 2.4, 4.26, 2.4, 4.26, alright, and you'll see we have all of them there. I was just checking the first couple to make sure that we got the right columns. Alright, so, now, so if you remember from the Antoine equation, it doesn't actually deal with pressures, it deals with the log of pressures. So we're going to want to make a variable for the log of pressures. We can call that p p underscore log. And we're going to have that is we're going to use numpy log 10 of the pressure. Yep. So then p log will be the logarithms of all those pressures. Alright, so now maybe we want to plot this just to see what it looks like. So we're going to add a figure. Figure 1 equals make subplots. Alright, and then we're going to want to add subplots. So it's fig1 dot add scatter, because we're going to want a scatter plot for this because this is, random data or raw data that we have, and it's going to have some random error associated with it. And we're going to want, so the x values are going to be our temperature, so x equals temp. Our y values are going to be our logarithm of our pressure, so p log. And then we're going to want mode, so that's going to tell us, if we have a line, if we have points, and that sort of thing. So we're going to want specific points for these data, not lines connecting the points. So we're going to go, so that means mode is markers. And then we're going to want to label this data, so name equals data. Shift enter. Alright, and now you can see we've got a plot of our data. So it looks good so far. Alright, so the next thing we're going to want to do is define a function that will take the sum squared error of all of these data points. So we'll define the function, we'll call it SSE for sum squared error, and this function will need an input, so we can input v, and then let's define what v is. So v is going to be our guess for a, b, and c, and a, b, and c are the constants in the Antoine equation, and we have to input a guess so that Python has something to work with, but it doesn't really matter what we input. So let's unpack the vector v, and we're going to call it a, b, and c is equal to b. Right, and then now let's actually write out the equation for the sum squared error. So you'll remember when I was describing before how to do the non-linear regression, I ended up with something that was y minus y sub I. And y sub I was our y values of every single data point. Well, we have these already. These are our p log values. So we can replace yi with p log. And then our y values are going to be what our function calculates as the log of the pressures. So that will calculate it by the Antoine equation. So we can replace this with a minus b divided by c plus t, right? Oh, but not t, because we called our temperature temp. So we're going to write temp instead of just t. And then we're going to want to square this whole thing to make sure that both positive and negative errors both get counted and that they don't end up canceling each other out. Alright, and then we're going to want to take the summation of all of the errors for all of the different data points. We can do that with the np.sum command. And then we're going to want our function to return this value. So we're going to type return. Alright, so now we have our function defined. Now let's work on minimizing it. So we can do this using the minimize command. So we're going to minimize, and what do we want to minimize? We want to minimize the SSE function. And we're going to need an input, and so these, again, are going to be random guesses for A, B, and C. So let's just go with 1, 2, and 3. Alright, let's shift enter and see what we get. Alright, so you can see that it outputs quite a lot of stuff. We don't really care about any of this stuff except this array down here at the bottom. And this array gives us the values for A, B, and C that Python has determined using this minimize function. So how can we just get this? So it's called x. So if we put .x here, it will return just the array. All right, so that's great, but now we want to get each of these values into its own separate variable. So we can unpack that by going a comma b comma c is equal to the minimize function. Shift enter, and we can check that that worked out. So a is 10, about b is about 1700, and c is about -36. All right. So now let's plot our function. So we're going to want to keep the raw data plotted, but I'll make a new figure just to make things more clear. So I'm just copying the commands that we used to make this figure appear and changing it to figure 2 because this is a new figure. And as you see, when I shift enter, I get the exact same thing because I haven't added anything new. But now we want to add our model to this plot. And so we want to do fig2.add scatter. Okay, so what are our x values? Our x values are going to be our temps, same as before. And y values this time are going to be what our model calculates. This is the Antoine equation. So we're going to have a minus b divided by c plus the temperature. Right. And then this time our mode, we're going to want lines because this is a model and not individual data points. And then we can name this and call it nonlinear regression. Alright, let's see how that looks. Alright, so here's our plot. As you can see, our model does fit the data fairly well. There's going to be some error in some of these data points, but it's still a pretty good fit. But another thing you will notice is that it's kind of choppy. It seems like it's just connecting the dots, because that's what it's doing. For the x values we've said that they're temp, and these are just the x values of these data points, so it's not calculating anything between, say, these two data points, it's just connecting the dots. So one way we can make our curve look a little bit smoother is to introduce a new variable. So we're going to call this t-plot, because it's like the temperatures that we're going to plot. And we're going to use the np.linspace command, because that is going to return a vector of linearly spaced data points that we can use to plot. So where do we want this to start? We want this to start maybe around 250-ish. So 250, and let's see, what do we want our final value to be? Maybe like 700? So 700, and we want maybe about 100 data points. And then we're going to want to use t-plot to plot this regression instead of temp, because there will just be more x values in t-plot, so the curve will appear smoother. Alright, so let's see how that looks. And there you go. We've got a nice smooth curve that fits our data pretty well. And that's how you do a nonlinear regression of the Antoine equation. Alright, so for the next part of this problem, we're going to want to take the linear regression of the Antoine equation, which I have written right here. Now, you can see the immediate problem is this is not a linear equation. So we're going to have to transform this equation into a form that it can be done with linear regression. So, just real quickly, so a linear equation is obviously y equals mx plus b, and linear regressions are done when you have a matrix multiplied by a smaller matrix to equal another matrix. So the smaller matrix is going to have to be a matrix of your unknowns. So in this case it would be m and b. Then you're going to have to multiply that by something. So in this case we've got, you can see it's m times x. So the first row is going to be our x values. We're down to xn. So these will be your x values for your data points. And then it's going to be b times 1. So you'll have a column of 1s like that. And it will equal your y's, which are also from data that you've taken experimentally. So this is the form that we're hoping to get this into. So I'm going to grab a different color so it's more clear. So you can see that's not quite in that form yet. So I'm going to show you how to get there. So first problem I see is this logarithm. But that's an easy fix because we can say that the log base 10 of p is just its own variable. So we're going to call this maybe p sub log. Alright, so p sub log is equal to the log base 10 of our pressure values. So yeah, these are pressures, T is temperatures, and then A, B, and C are constants. Alright, so might as well just rewrite it like that. So P underscore log, so that's the logarithms of our pressures is equal to A minus B over C plus T. Alright, so then the next problem I see is this fraction. So easy way to get rid of the fraction, multiply the denominator by both sides. So we multiply both sides by C plus the temperature. Right, and then we're going to write that out. So we'll end up with C times P log, so C times the logarithm of our pressures plus temperature times the logarithm of our pressures equals AC plus AT minus B. Because of this, we'll cancel out. Alright, so we're getting closer, but we're still not quite there. So we're going to want to get all of our unknowns on one side of the equation. So we can see this one has an unknown. Okay, we should write out what our unknowns and knowns are, just to make that clear. So we know our knowns are going to be the temperature and the pressure. So these are going to be experimental values that are given to you, or that you've taken from an experiment of some sort. And then our unknowns, I can't spell, hold up. Our unknowns are going to be A, C, A, B, and C, right? So we're going to get all these unknowns on one side. So that has an unknown, that has an unknown, that has an unknown. This one does not, and that term does. So, we're just going to subtract that over to here. We have T, or the temperature times the pressure of our logarithmic pressure is equal to, okay, so we're going to take AT, and then we're going to have minus C P, or pressure logarithmic, just so we can have the two with known terms in them next to each other. And then we need plus AC minus B. Alright. So we're getting closer. We can see that this is going to be our Y, because it's something we know, and it's by itself on one side. And then we can see that these two terms are going to be like our MX, because we've got an unknown times something we know. And then we've got two terms here that are sort of like our B. And we can combine these kind of into one unknown. We'll call it D for now. So another unknown we have is D. And D is going to be equal to AC minus B. Okay. So then I'm going to rewrite that, and I'm going to flip the sides so that matches up with the matrix that we're going to make better. So we're going to put this side on this side of the equation. So AT minus C times the log of the pressure plus D is equal to temperature times the log of the pressure. Alright. So now we can set up our matrix. We'll have one big matrix times the smaller matrix is going to equal another larger matrix. Alright, so small matrix we can call our vector. This one is our design matrix. And this one we can just call lowercase b. So, or no, that kind of gets confusing with that, so we're going to call it something else. We'll call it R. Okay, so this middle vector we're going to have just our unknowns. So the unknowns we see are going to be A, C, and then D. And then later, once we get the D value, once we solve for the D value, we can come over here and find the B value because we'll solve for the A and C as well. Alright, so then it's going to be A times the temperature. So I have our first temperature, second temperature, all the way down to our nth temperature. So n is just the amount of data points that you have. And then we're going to have our first pressure logarithmic, our second pressure logarithmic, all the way down to our nth pressure logarithmic. Right? And then make that a little bit bigger. And then for the D, we're going to have our column of 1s just like we had up here. We're going to have 1, and all the way down to 1. Alright. So then, this is going to just be equal to T, the temperature, times our logarithmic pressure 1. So that's temperature 1 times logarithmic pressure 1. And then temperature 2 times logarithmic pressure 2. All the way down to temperature n times logarithmic pressure n. Alright, so this you can see is an n by 3 matrix. This is a 3 by 1 matrix. This is not a 3, an n by 1 matrix. Alright. Alright, and then we can write these off kind of in variable form. So like a design matrix, we'll call that dm, times the vector, we'll call that b, is equal to r. And you can see based on the size of the vectors that if we multiply it how it is, it's not going to get us the right size of our vector. So to do that, we're going to want to take the transpose of this matrix, so you basically flip it sideways, and we're going to want to multiply that by both sides of the equation. So we'll call that dmt. So I have dmt times dm times b equals dmt times r. And then we're going to use that equation to solve for our linear regression. Alright, so the final part of this problem says transform the Antoine equation such as to enable linear regression. So I've showed you how to do the transformation already, and I've attached this screenshot of how the final transformation turned out to be so that we can reference it as I show you how to code this in Python. Alright, so I'm going to use the same notebook that I used for the nonlinear regression because we already have the libraries imported, we already have the data imported, so I don't have to redo that. We can just use the same thing, but I've included a linear regression section down here to differentiate it from the nonlinear part. Alright, so the first thing we're going to want to do is input our matrices. So our first matrix we want to look at is the design matrix. So we can call that dm. And we're going to use the np.c underscore command to create this matrix. So the first column in this matrix are our temperatures. So let's put those in. We called them temp up above when we loaded in the data. You can see, and our photo pressure is p underscore log. So we input our temp, that's the first column. Okay, second column is going to be the logarithms of our pressures. And I notice now that I may have forgotten to write this negative sign right here, down here, but it should be there because you can see that it's a negative c times p of log, and so we're going to need a negative sign down there. So I'm going to include it in the code even though I forgot to write it here. So negative p underscore log. So that's the negative logarithm of our pressure. And then the final column that we have is going to be a column of ones. So we can use the np.ones command. And then we're going to need to specify, the shape of this vector. So, Python knows how many ones to put in that column. And we're going to use the underscore like command, and we're going to make it the same shape and size as our temperature vector. All right. So that's the design matrix. The next matrix that we're going to look at is this R. And the R's are just the temperatures times the logarithm of the pressures. So R is equal to the temperature times the logarithm of the pressure. All right. We'll shift enter on that. So now we have our two matrices, and we're going to want to go about solving these. So for that, so this is an overdetermined system of equations, which means we have more equations than we do have unknowns. And so we're going to use the np.linalg.solve command, and we're going to need to put two arguments into here. So the arguments we're going to want is this design matrix transpose times the design matrix, and then the design matrix transpose times the R vector, and this will get us out our V vector. So let's do that. So we've got design matrix dot T, so that's the transpose. We're going to use the at symbol as a matrix multiplication as opposed to regular multiplication. So times the design matrix, that's our first argument. Second argument is going to be the design matrix transpose matrix multiplied to the R vector. I'm going to shift enter. Alright, so you can see we've got some values. Alright, so this array that it gave us out is it solved it for us. And so this is the vector v. So we can put that into v1. I'll use v1 to differentiate it from when we used a v up here. So v1, and so then we can see the values for v1, and you'll notice that some of them look familiar, because remember from up on our nonlinear regression, we had A, we had B, and we had C. So you'll notice that the first value here looks very similar to A, as it should, and the second value looks very similar to C, but you'll notice we don't have B here. And that is because, if you remember back to the vector we're trying to find, it's actually going to give us out A, C, and D. So we're going to need to solve this last value, D, for B. So, D is equal to AC minus B, which means that B is going to be equal to AC minus D. So we can do that. So, but first we're going to want to split these up. So, we're going to want to unpack them so that they're in their own values. So we can do that by A1, B1, or A1, C1, and D1. And again, that's just differentiate from these A, B, and C from before. Alright. So then we can see that A1 is 10, C1 is negative 34, and D1 is negative 2000. Alright. So we're going to want to find B1. So B1, or B is going to be equal to A times C minus D. So let's type that in. So it's going to be equal to A1 times C1 minus D1. Alright, and then let's check what we get for B1. And there we go, we have 1,700, and we have 1,700 from our linear regression. So you'll notice the values are not exactly the same, but they're pretty close. So the only thing left to do is plot it up and see how it looks. I'm going to reuse the commands from before, just so I don't have to type everything out again. and then I'll just change them slightly. So obviously this is going to be figure 3 instead of figure 2. And then, so these two, we're plotting our raw data, so we can keep those the same. And then this was, we created a vector t plot, which are, t values, temperature values, to make the curve seem more smooth, so it's not just connecting the dots. So we can leave that there. And then what we're going to want to change is, instead of using A, B, and C from our nonlinear regression, we're going to want to use A1, B1, and C1 from our linear regression and change this name to linear. So we shift enter on there, we can see we get the plot, and that our model fits the data pretty well. And so that is how you do a linear regression of the Antoine equation.